All right, as a reminder of what an LC circuit looks like, we have a capacitor, we have an inductor, and there's initial energy inside of the capacitor that is going to get swapped back and forth between the inductor, so energy bounces back and forth. You have energy due to the electric field inside the capacitor. You have energy due to the magnetic field inside the inductor at any specific time. And these energies change. However, altogether, this is equal to a constant. So because we have no energy loss, there's no resistor in this type of circuit. So this is the total energy, and if we were to write it out, this would be Q squared over 2C plus 1/2 Li squared. So hopefully that's not a surprise to anybody. What we did previously is we said, since the energy is equal to a constant, then du dt has to equal 0. And we went through and we took the derivative of this and set it equal to 0. When we did that, we ended up with an equation that was a second order differential equation that looked like this. There. And we did not try to solve this one, we just said what the solution was. The solution looks like this in general. Q equals big Q times the cosine of omega t plus phi, like that. And just to make sure that this was a solution though, we went back and we took the second derivative of Q, plugged it in here, took the function itself, plugged it in here, divided by LC, and whenever we worked through that problem, we found out that yes, this is indeed a solution, but it's only a solution if omega is equal to 1 over the square root of LC. In other words, if the frequency of the oscillation of the charge on the capacitor is equal to this, then Q, as written here, is a solution for the second order differential equation. Okay, this then is the frequency of oscillation for this circuit here. It's called then the natural frequency. The natural frequency is the frequency of oscillation at which this circuit will naturally exchange energy. In other words, this is an oscillator, this is a simple harmonic oscillator, and it has a natural frequency that is related to the value of L and the value of C. So you could choose L and you could choose C values for these two components here, and what you could do then is you could make this natural frequency be pretty much anything you wanted to, if you wisely choose values for inductance and capacitance. So choosing those values means that you can set up any natural frequency. All right? That natural frequency then is sometimes, and the resonant frequency is the frequency at which very little expenditure of energy is needed to cause an LC circuit to oscillate like that. All right? Now, when we add in a resistor here, we add a resistor into our circuit, then at that point, the natural frequency doesn't change. So the natural frequency of the circuit is really set up by the value of L and the value of C. Adding the resistance in means that we have a loss of energy at a rate of I squared R, but that loss of energy doesn't affect the natural frequency. The loss of energy affects this Q, the maximum amplitude of the oscillation. However, it doesn't affect the oscillation itself. All right? So I want you to get that lesson here. The lesson here is that the natural frequency is controlled by the L and the C. All right? All right, so the natural frequency is the frequency at which the LC is going to drive the circuit to be. And that frequency is given by omega naught is equal to 1 over LC. Let's distinguish this from just any frequency and put a subscript 0 on there. So omega naught is the natural frequency defined this way for an LC circuit. All right. Now, so far, everything we have done has not included a source. This circuit really becomes interesting when we have a source that is a time-varying source. So let's say that we have a source, and we're going to write a source like this, circle with a little sinusoid in it. This is going to be a sinusoidally varying source, all right? And we're going to hook it up to an R, an L, and a C. There. We can put a switch in here if we want to turn it on, but you get the idea. There's going to be some EMF source that is sinusoidal in nature that is hooked up to now an RLC circuit. Okay, if we were to write out what the equation for E looks like, since we know it's going to be a sinusoidal variation, E is equal to some maximum value times the sine of omega t. Now we could have written cosines here, but for some reason your textbook decides to use sines, so I'm going to stick with that. Now this omega, that's the angular frequency of the generator. Now I drew it as a sinusoid here. An example of this type of time-varying source could be like wall power. You plug into a wall, it has a certain frequency. Now the frequency is usually in America 60 hertz. But the omega here is the angular frequency, and the relationship between this frequency and the angular frequency is given as 2 pi f is equal to omega. All right, so you take this 60 hertz, multiply by 2 pi, and that gives you what omega is. And omega in the US turns out to be something around 377 hertz. Okay, so that's the frequency of the generator. Now, the frequency of the generator here, in general, keep in mind, this is only for US wall power, okay? That's not necessarily every frequency source. So in general, this is not equal to the angular frequency. In other words, the angular frequency, omega naught, which is 1 over the square root of LC, is not always guaranteed to be the same as the omega of the generator. So the frequency of the voltage source, though, this frequency here, is going to be the frequency at which things change. In other words, if there's a current here through these wires, through this circuit, that current is driven by the voltage source. That current may be affected by omega naught, but omega naught is not a thing that has energy. Remember, these are passive elements here. They cannot drive a frequency unless power is supplied from someplace. If the power is supplied from a voltage source that has a frequency of 377 hertz, then 377 hertz is going to be the frequency at which the current changes. So if we have a time-varying voltage source, that's going to set up a current. And that current we can call I, and that current is going to have some I max times the sine of omega t plus phi. All right, now that angle right there, the omega t, I'm going to change this because the textbook writes it this way. The textbook writes it as minus phi. All right, I'm doing that solely to stick with the textbook notation here. But that phase angle phi that's found here is not necessarily the phase angle of this. The way that we've got the EMF written for our voltage source, the phase angle is 0. So in other words, we're using the 0 as the reference out of which the phase angle phi is being written, and that changes that to a negative sign. So just using the notation, that is a negative sign there. But my point here is, I'm going to have a current, and that current, if you look at the equation here, that current is sometimes going to be positive and sometimes going to be negative. What does that mean? That means the current's going to go this way sometimes and the opposite way other times. This way, that way, this way, that way. But we draw it in one direction and just say the current sometimes is positive in this direction and the current is sometimes negative in this direction. So we just draw one direction here, but we realize this is an alternating current. This is what is known as AC current. So the current alternates, and the voltage source also alternates. So the voltage alternates as well. But here's the point, and this is, I've kind of belabored this, but I want you to get this. The frequency of the source is the thing that drives the frequency of the current. And if you look here, you'll see that this omega is the same as that omega. So the source voltage and current are exactly the same regardless of what this is. All right? Now here's something you need to realize as well. This amplitude here, I sub m, is affected by whether or not omega equals that, omega naught. The source frequency is not necessarily the same as the angular frequency, but if the angular frequency and the of the natural frequency, let me say that again, if the natural frequency is equal to the frequency of the source, then I sub m will be maximized. In other words, you're going to get out the maximum current if these two frequencies are equal to each other. So if you set your frequency for your source equal to the natural frequency of the circuit, that's the frequency at which the R and the L and the C naturally oscillate. If you set your frequency of your source equal to that frequency, then you're going to get out the maximum possible current that you can. Otherwise, you're going to be limited in current. The maximum I sub m is going to be reduced. So, if you created some type of a plot, and let's say you drew it like this, and this is the omega axis, and this is I sub m values. And this represents omega naught. And you have the ability, let's say, to tune the frequency of your source here. So you have the ability to change omega. So it's not fixed at this value the way it would be for a wall socket. This is some kind of special generator that you've built that allows you to change frequency. So if you want to measure what I sub m is, it'll be down here somewhere. There might be some noise and it might wiggle around a little bit, but it's going to be right around there until you get to omega naught. And then at omega naught, this goes up really high and then comes back down for frequencies that are higher than omega naught. So this is what is meant by the resonant frequency. If you can make your generator frequency omega equal omega naught, then you're going to get out the maximum value for I sub m that is possible. And at that case, if you do that, then you have a case of resonance. You have set your generator frequency equal to the resonant frequency of the circuit itself, and that creates the maximum output for I sub m. All right. Now, I itself is still time varying, but I sub m is maximized, so you get the maximum amplitude out of this sine wave then. Okay. So with that, here's what you notice. This is amplitude. This is angular frequency, the same angular frequency of the source, and this is the phase angle. All right. This is the type of circuit that we want to be able to solve. All right. But in order to solve that, you need a little bit of background. So let's develop that background right now. All right. So I'm going to redraw the circuit one more time. There it is. Time varying source, resistor, inductor, capacitor. E, R, L, and C. We know that E is going to have this general form, E sub m sine of omega t. And if you're given a problem, those things are usually given to you. The things that are given are E sub m and omega, and you know the general form of it. So let's apply KVL. So we're going to apply KVL to this, and you'll notice that these are all in series. We only have one current then. So E, this, the voltage of the source, which is time varying, but for any time, the voltage of the source has to equal the voltage across the resistor, plus the voltage across the inductor, plus the voltage across the capacitor. That has to be the case. And that will be true for all times. So E is E sub m sine of omega t has to equal Well, V sub r, that's just I times r. Of course, I is going to vary. We need to set up this equation, and when we set up this equation, perhaps we can solve for I, plus L di dt, plus the voltage across the capacitor. Now we need to figure out what the voltage across the capacitor is. Well, if you recall the capacitor equation, let's write it over here. Q equals C times V. All right, if we take the derivative of that, dq dt, that's equal to C dV dt, and dq dt, well, that's just I. So here you have the relationship between current and voltage for a capacitor. All right, if I take this and I separate the variables, then let's write this as 1 over C times I times dt is equal to dV. And this V is the voltage across the capacitor, so I'm going to put a subscript C on it so it matches our notation here. Okay, what we need to do in order to solve this and figure out what the voltage is we need to integrate this. And when we do that, we integrate this side as well. On the right-hand side, this is just the voltage of the capacitor, V sub C, when we do the integral. But over here, 1 over C times the integral I dt, we don't know what this is unless we have some function for I. So what goes here is this integral, 1 over C times the integral I dt. All right, now this is not a math class, so we don't know how to solve this problem, but I'm trying to convince you here that this is the way you would get to a solution, and you would write the solution as I equals some function of time. This equation here is not one that we are able to solve. It's a little more difficult, but look, it is a difficult equation because it's got an integral in here and a derivative in here. So it's difficult. That's the point. So that's why we're going to jump straight to the solution and write the general form of the solution this way. I times the sine of omega t minus phi. So there we have the general form of the current that's going to be set up in this circuit whenever it's hooked up and activated. So the whole point of this exercise was to show you that when we have a circuit, an RLC circuit, a series RLC circuit like this, the form of the voltage is this, the form of the current is this, and once you have the current, you can figure out what the voltages are across all of the elements. For example, what's the voltage across the resistor? If I know what I is, then the voltage across the resistor is just this right here. You just take I multiplied by R and you've got your answer. Let's say you want to know the voltage across the inductor, V sub L. Well, once you've got I, you take the derivative of it with respect to T, you multiply by L, and there's your answer. That's the voltage across the inductor. Well, what about the voltage across the capacitor? Same idea. You take your I value, you plug it into the integral equation here, and you've got your value for the voltage across the capacitor then. So the key to solving this kind of circuit is to figuring out what I is. But there's really only two parts missing from I. For example, you need to know what big I is, and you need to know what phi is. Those are really the things you need to figure out in order to figure out what I is. Now, why not omega? Why do we not have to figure out what omega is? Because this omega is exactly the same omega that the voltage source has. So whatever the voltage source is, that's what the current frequency is going to be. Okay, those two things go together. All right, what we're going to do is we're going to solve this using phasors. Now, phasors are not the kind that's in Star Trek. Phasors are something very similar to a vector, and you'll see as we get farther into this exactly what that means. Now, in order for you to understand this, the textbook goes through a lot of mathematics to convince you of the reliability of phasors. I think you guys can trust me on this. Phasors are going to work, and we're going to be able to solve the circuit with phasors. But you need to understand a few more things here. So let's make a little table. Let's make a table that's going to be useful to us when it comes time to solve that RLC circuit. Let's make a table for R, for C, and for L. So these represent the different elements, so we could label this column element. Okay? Now we're going to have impedances. Impedance, since we're talking about an alternating current now, resistance is really something that we learned in a non-alternating current world, so in a DC or direct current world. But now that we're talking about alternating currents, we're going to talk about, instead of just resistance, we're going to talk about impedance. Now, resistance is a type of impedance. But what is impedance? Impedance is defined as the opposition to AC current flow. The same way that resistance is defined as the opposition to current flow, back when we were talking about only DC currents. Well, now that we're talking about AC currents, you need to know that the more encompassing term for resistance is actually impedance. So resistors have an impedance that is nothing but the resistance value. So resistance is a form of impedance. When it comes to capacitors, though, and inductors, the impedance is called a reactance. So we have something that we're going to call X sub C. And what is X sub C? X sub C is capacitive reactance. And X sub C is defined this way: 1 over omega C. So this omega is the frequency of the generator. So you can see that how much a capacitor opposes AC current flow is related to the frequency. If you increase the frequency, make this number on bottom bigger, then you make this smaller. So it offers less opposition to the current flow at very high frequencies. All right, when it comes to inductors, we're going to define something called X sub L. And inductive reactance is defined this way: omega times L. So you can see here that inductive reactance, the opposition to AC current flow from an inductor, is related directly to the current. So if you increase the frequency, it's related directly to the frequency. So if you increase the frequency, you increase the amount of opposition the AC current feels from an inductor. So you can see these two things are kind of opposites of each other. Increase the frequency here, X sub C gets smaller. Increase the frequency here, X sub L gets larger. Resistance is not dependent upon frequency at all. It's just there. Okay? Now the next thing we need to talk about is something called phase. The phase angle. Now you've seen that phase angle pop up whenever we were talking about current here. So that angle is the angle between voltage and current here, but it is affected by these impedances. So what if you had just a solely resistive circuit? Now this is for an only resistive circuit. The phase angle is this, that I is in phase with the voltage across the resistor. So the current is in phase with, that's not an omega, that's with the voltage across the resistor. All right, so what does that mean? That means the phase angle for a solely resistive circuit is 0 degrees. And that's the phase angle. What about the amplitude? Well, the amplitude can be given by this equation. V sub R equals I times R. That I is the amplitude of the current. This V sub R is the amplitude of the voltage across the resistor. All right. Remember, I'm reminding you, if I wanted to figure out what V sub R is, I just take I, which is I sine omega t minus phi, and I multiply by big R. So this is the voltage across the resistor. So it's equal to V sub R sine omega t minus phi. That's the equation then for the voltage across the resistor as a function of time. But this V sub R is the amplitude. It's the amplitude of the voltage across the resistor. And that capital V sub R is what this is. All right? So for a totally resistive circuit, the current and the voltage are in phase with each other. That means the phase angle is going to be 0 and the amplitude is going to be just I times R. All right, now if you do that same sort of thing for capacitor and inductor, here's what you find. You find that current leads the voltage across the capacitor by 90 degrees. So I leads V by 90 degrees for a solely capacitive circuit. So that makes the phase angle negative 90 degrees. It's negative because of that negative sign that's in there. And the amplitude of that equation would look like this. V sub C is equal to I times X sub C. So this equation here for the amplitude looks an awful lot like the equation for the amplitude for resistance, which itself looks an awful lot like Ohm's law. And if we're dealing with just amplitudes here, you can treat that like Ohm's law. All right. So this X sub C, you can see it is very much plays the same role as resistance does. Now, if we do the same thing for a solely inductive circuit, this middle one was for the solely capacitive circuit. If I said it any other ways, I was wrong. It's for a solely capacitive circuit. Then for a solely inductive circuit, I lags V sub C by 90 degrees. And that makes the phase angle plus 90 degrees. So V sub L equals I times X sub L. This is a table that's going to be useful to us then whenever we start solving for the series RLC circuit. Okay? A couple of things here to help you memorize this table. First of all, impedance is the opposition to AC current flow. So you can think of R, X sub C, and X sub L as all being components that are opposition to AC current flow. The X sub C and the X sub L depend upon omega, but you can see that one's an inverse relationship to omega and the other one's a direct relationship to omega. But this stuff about the phase about how a resistive circuit is the I and the V are in phase. Here the I leads, here the I lags. The amount they lead or lag is always 90 degrees. How do you remember that? Well, here's the way you remember it. Since V sub C is the same as EMF, and this is V sub L. It might my L look like a C there. So this is EMF. So remember it this way. ELI. For an inductive circuit, that's one with an L value, the EMF is ahead of the I. That's another way of saying that I lags the voltage. So the EMF is ahead or leads by 90 degrees. And then the other mnemonic is ICE. For a capacitive circuit, the current leads the voltage by 90 degrees. So you can remember this as Eli the Iceman. And that mnemonic will help you remember for an inductive circuit, the voltage leads. For a capacitive circuit, the current leads. And that bit of information will be useful to us later on. and I will show you why when we start drawing phasors. All right, I'm presenting this table to you right now so that you can have that under your belt. You can use this. You should use this table when it comes time to solve circuits. All right, so let's talk about a circuit. So once again, drawing the series RLC circuit. There's the R, there's the L, there's the C. So there's my EMF, there's the R, L, C values, and we're going to have a current of setup of I. Now there's only one current here, and if we traverse the loop, you know that E equals V sub R plus V sub C plus V sub L. This equation is true for all times t, and you know the solution for that is of this form: I equals big I times the sine of omega t. Keep doing it. That's a negative sign, that's a negative sign, phi. There. So let's plot the current on a phasor diagram. So here's what a phasor diagram is. It's really a rotational diagram on which we can put vectors. Now, for the current here, the current has two parts. It's got an amplitude and it's got this angle. All right. So if I draw it on here, I draw a vector. The length of that vector is the magnitude. And the angle here is the angle omega t minus phi. Now you can see that as time changes, this angle is going to change as well. In fact, this whole vector is going to rotate around on this scale here. The projection onto the vertical axis here is going to change. So at maximum, you know, when this vector phasor lines up with the vertical axis, the maximum is going to be big I. But at anything less, at another time down here, the projection onto the vertical axis is what I is, little I. So it's the instantaneous current for any time. As time goes by, it's going to rotate around like this. So at some time down here, you're going to have a phasor that points down here. The projection onto the vertical axis is also going to be little I, but in that case, little I will be negative because it's down here. All right? So I've just drawn I at some arbitrary angle. I'm just drawing it in this quadrant, assuming that the angle omega t minus phi is in this first quadrant right here. All right, and that's solely for convenience because you understand this is going to move. This is a living phasor that's going to move. The angle is going to change. The length is going to remain the same. Now, based upon our mnemonic, Eli the Iceman, we can add the phasors here for V sub R, V sub L, and V sub C. Now keep in mind, let's add V sub R first. V sub R is this phasor, and that phasor. So the phasors are the amplitudes. The phasors are the amplitudes of each of their voltages and currents. All right. Now for the R, we know that the current is in phase with the voltage. So V sub R is going to be in phase with this. So if I draw V sub R, it's going to be right on top of this current vector. So I'm going to make it a little thicker there. That arrow there indicates V sub R. Now I don't know if it's shorter or longer, but I'm drawing it on top of it. The projection onto this vertical axis, that's what little v sub r is. So little v sub r indicates the time varying voltage. Big V sub r here is the fixed value. That's the amplitude that's not going to change. So what does that mean? The voltage across the resistor is equal to big V sub r times the sine of omega t minus phi, and this angle phi is the same as what that angle phi is. So that's what that means. Now, for V sub L is going to be capital V sub L times the sine of omega t minus its phase angle. But its phase angle is not necessarily the same as this phase angle. In fact, it won't be. Okay? If we call this theta sub r and this theta sub L, then those are different. And we can do the same thing down here. V sub c sine of omega t minus its phase angle sub c. All right, but those phase angles you know. These phase angles are these numbers here. So phi sub r, that's 0 degrees. All right. Now, that's 0 degrees relative to the current. So the voltage and the current are right on top of each other. So whatever the current phase angle is here, that's what this phase angle is. So this 0 degrees is relative to that phase angle. All right. Now, these are going to be 90 degrees relative to the phase angle. So negative 90 degrees and plus 90 degrees. So we've put V sub r on here. Then we should be able to, based upon our mnemonic, Eli the Ice Man, for the next component, we should be able to add that. Well, let's add the L. We've already done V sub r. Let's add V sub L. Well, V sub L, we have a inductive circuit. That means the voltage is ahead of the current. And how much is it ahead? By 90 degrees. Okay? Oops, we're doing L, so plus 90 degrees here. Okay? So if I draw that on here, that needs to be drawn up in this direction. And I'm saying that that is V sub L right there. And this angle here from there to there is 90 degrees. The projection of this onto the vertical axis, well, that is V sub L at any point in time. And this whole system is going to rotate it together as a system. And now I can put V sub c on there, and V sub c is going to be in the opposite direction at negative 90 degrees. So let's draw it right there. V sub c, once again, this angle here is 90 degrees. All right, so what we have done here is we have put all of these together on one, what's called a phasor diagram. All right, now comes the tricky part. Notice that we've got V sub r, V sub c, and V sub L, and that has to equal to this. This is also, we can treat like a phasor. All right? But this is just an algebraic sum. Down here, the phasors have to be summed up as you would a vector, but we would call it a phasor as we would a phasor. So when we do this, I'll show you the trick. Let's take this, and you notice that V sub L and V sub c are always going to be in opposite directions from each other. So if I redraw this, I'm going to draw it this way. There's my big I one more time. There's my V sub r that's right on top of it. And now I'm going to draw one vector here that is V sub L minus V sub c. And we can do that because we know that they're always going to be in opposite directions from each other, so we'll write it that way. Now, the reason for doing that is because all of these added together. So we added these two vectors together by subtracting that one because they're always in opposite directions. But it's really a vector sum of those. So think about this. The vector sum of V sub r, V sub L, and V sub c is going to create a resultant. I'm trying to draw a nice rectangular dashed lines here so that I can draw my resultant. There's the resultant vector, and that is E sub m. Okay, and where does E sub m come from? Well, it comes from E, because E is E sub m sine of omega t. So it's that right there. Now look at this. This is a vector sum because we can say that E sub m squared is equal to V sub R squared plus V sub L minus V sub C squared. So you can get, that's just a recognition of this vector sum here, which is just a statement of what you know from up here. The algebraic sum of these is the same as the vector sum of these, of these three things, the vector sum of these three things, which is equal to that. So the vector sum of that is equal to this vector plus that vector plus that vector. That's the same sort of statement as saying this algebraic value, the instantaneous value for E sub m, is equal to the instantaneous value for these three voltages. So that's a general statement regarding vectors, that you can say that this sum and these sums are the same. But when you sum up your vectors, you have to sum them up like you would a vector. So the magnitude of the E vector, which is E sub m, is given by this. All right, now follow through here. Capital V sub R, that's big I times R squared, plus V sub L, that's I times X sub L minus I times X sub C quantity squared. And you'll notice here that we can get rid of some i's here. We'll solve this for I. In fact, let's factor out the I and solve for I. And when we do that, we're going to get I equal to, well, E sub m squared. No, it's just E sub m divided by the square root of R squared plus X sub L minus X sub C squared. There. That's an important piece, because here you have the ability then to find out what your I is. Remember, the unknowns here are the big I and that phi. So we've just figured out a way to get the big I here. We get the big I from solving this equation right here. And if you'll look, what's on the bottom here is called the impedance. It's just the impedance, and we'll give it a new symbol here, Z. Z is equal to the square root of R squared plus X sub L minus X sub C squared. So when you add up all of the impedances, and that's what we're doing down here, we're adding them like a vector to figure out the magnitude of them, then this becomes an equation that's just E sub m over Z. And remember, if impedance is like resistance, then this is very much like I equals voltage over impedance or resistance. Okay? In a DC circuit, there would be no frequencies, so there would be no values for X sub L and X sub C. So the impedance would be only the resistance. All right, so we've got an equation then that's going to allow us to find capital I, which is half of the puzzle. If we were to rewrite that equation, we could rewrite it in terms of the omegas. So capital I is equal to E sub m over the square root of R squared plus, and now we could write it as omega L minus 1 over omega C squared, like that. Just another way of writing it, E sub m over Z, same thing. All right? Now, I've got capital I, so I've got the maximum value. Now, think about this. Remember, I said at the very beginning back here, I talked about resonance. And I said, if you can set the omega of the generator equal to the omega naught of the circuit itself, the resonant frequency of the circuit, then you're going to get the maximum value out of the amplitude for I. And I called that I sub m here in this equation, but it's changed its notation to just be capital I back here. All right? Well, when is this capital I going to be maximized? If you look at this equation right here, capital I becomes the greatest when what's on the bottom of the fraction, when the denominator down here, is the smallest. So when is the denominator the smallest? Well, the denominator is the smallest when, well, R could go to 0, but then you don't have an RLC circuit. It's going to be smallest when these two things are equal to each other. All right. In other words, when omega L is equal to 1 over omega C, in that case then, this is going to be smallest. In other words, the radical on bottom is smallest and capital I is largest. All right, well, when does this occur? This occurs when omega is equal to 1 over the square root of LC. In other words, when omega is equal to omega naught, that's when you have the maximum value for your capital I. When does that happen? That's a case of resonance. So capital I is largest at resonance, when the frequency of the generator matches the frequency of the circuit itself. All right. Okay, we're halfway there. We've still got another thing that we need to solve for, and that is the phi. So let's do that pretty quickly, because I think now that you recognize the phasor diagram, you're going to see how easy it is to get it. So here's capital I. There's V sub R directly on top. This is the angle omega t minus phi there. We've got V, that's V sub L minus V sub C in that direction. And then the resultant is right up this way. Let's put it right here. I know it's a little messy, but that is E sub M. That's the maximum E sub M. Well, this angle here is phi. Okay? And the angle between V sub R and V sub L minus V sub C, that angle there is 90 degrees. All right, so the angle we're after is this angle right there. That angle there is omega t. Okay? So from what we know of the generator, we know that E is equal to E sub M sine of omega t. So omega t is the angle up to the E sub M. Now, from geometrical arguments then, we're after this phase angle phi. We can just say that the tangent of phi, look at it carefully here, is going to equal to V sub L minus V sub C over V sub R. That's this angle here. The side, it's opposite over adjacent. That's what tangent is, opposite over adjacent. So we've got this right here. All right, we can rewrite that as I x sub L minus I x sub C over I R, and then the i's will cancel, and we're left with tangent of phi is equal to x sub L minus x sub C over R. There is the other equation. So now we have two. We've got our two unknowns. What we can do now is we can take these two things and put them together, and we can solve a problem. And that's what we're going to do now. Okay, one more thing before we do that though. If x sub C is bigger, then we have a capacitive circuit. If x sub L is bigger, then we have an inductive circuit. If x sub L and x sub C are equal to each other, then we have a case of resonance, and we only have a resistive circuit. So keep that in mind. X sub C is bigger, we have a capacitive circuit. If x sub L is bigger or larger, then we have an inductive circuit. All right? Keep that in mind. All right, let's go and say that we've got this RLC circuit. And let's give some values. Let's say R is 160 ohms. C is 15 microfarad. Let's make L equal to 230 millihenry. Let's say that our frequency here is 60 hertz. And the value of E sub M is 36.0 volts. The question is, what is I. What's the current? What's the current equation look like? Well, in order to figure out what the current equation looks like, we need to know what capital I is and capital Phi are. So it's really asking for those two things and then put it into this form. I times the sine of omega t minus phi. This omega is going to be the frequency of the circuit. And we know the frequency of the circuit, but we don't know the angular frequency. Nevertheless, omega is going to be 2 pi times f. Since this is 60 hertz, I know that one. That's the 377 hertz answer. All right. Okay, so now that we've kind of got all those pieces put together here, it's time to start solving. I is going to be E sub m over z. We need to know what z is first. Well, z is the square root of r squared plus x sub l minus x sub c squared. Okay, well, then we need to know what x sub l and x sub c are. You're correct. X sub L is omega L, and that's going to be 2 pi f times L. So you take this 377, you multiply it by 230 millihenry, so that's 0.23 Henry. You end up with an answer of 176.8, and the unit is ohms, because the unit of impedance, any type of impedance, is ohms. Okay, we need to know what x sub c is then. X sub c is going to be 1 over omega c, which is going to be 1 over 2 pi f times c. Take your 377, multiply it by that, take the reciprocal of it, and you end up with 107, oops, I did this wrong, I'm looking at the wrong number. This is 86.7 ohms, corrected. This is 176.8 ohms. There. Okay, so we've got our x sub l and our x sub c now. Let's go back to our z. We need to take square root of r squared, 160 ohms squared, plus x sub l, 86.7 minus 176.8, quantity squared, like that. That turns out to be 183.5 ohms. There. Now let me ask you, is this a capacitive circuit or is this an inductive circuit? How do you tell? Well, x sub c is larger. X sub c is also larger than r. So this is going to be a capacitive circuit. If it's a capacitive circuit, then what does that mean? Let's go back to our little chart. If it's a capacitive circuit, then the current is going to lead the voltage. Current's going to lead the voltage. Now, it's not going to be by 90 degrees because that's only for a purely capacitive circuit. But this will always be the case if you have a capacitive circuit, that the current leads the voltage. All right? So we should look for that. Let's get back here. I know what Z is, and now I can back up and I can figure out what my capital I is. My capital I is going to be 36.0 volts divided by 183.5 ohms. And that turns out to be 0.196 amps. So there's my capital I. We're halfway there to get a solution. Okay, let's go realize that phi is going to be the inverse tangent of x sub l minus x sub c over r. That turns out to be the inverse tangent of 0.564. So phi turns out to be, well, it's going to be 29.4 degrees, but it's going to be negative. There. Okay, now, is that the case? So I leads E. It should. So let's look here. What does E look like? Well, the equation for E is 36 times the sine of 377t. So it has a phase angle of 0. The unit there is volts. And then little I is capital I, 0.196 times the sine of 377t minus a negative 29.4 degrees amps. So I is in front of that one. And you can tell it leads because the phase angle is larger for I than it is for E. Remember, the phase angle for E is 0. So 29.4 is bigger than 0, and it's a positive 29.4. So there, we've got it. There. The I leads the E. And we're done. So, well, not quite. We've still got we are done. Here, I put it in that form already. This is the final answer because we were asked for what is I. This is the final answer right here. Okay. Now, let me caution you about something. This is a very common thing in the world of engineering especially, but it happens in physics as well. You'll notice, if you look carefully at this equation, there's something wrong with it. And the something that is wrong is this. You've got 377. What's the unit on that? Well, the unit on that is hertz. But this is angular frequency, so what kind of hertz are those? Those are radians, radians per second. So it's radians per second. When I multiply by time, time is in units of seconds. So this 377t is units of radians. What's the unit here? Degrees. So if you ever write it this way, that's an inconsistent way to write it. You need to either convert 29.4 to radians, or you need to convert your 377t to degrees, because you cannot add these things the way they're written. Nevertheless, this is exactly the way it's written a lot of the times. You'll see one expressed in units of radians, you'll see the other expressed in units of degrees. And for the life of me, I can't figure out why that's acceptable, but it is. It is acceptable, especially in engineering classes, that's the case. But keep that in mind. If you had to determine the specific value for I at t, let's say t equals 30 milliseconds. If t equals 30 milliseconds, what's I? Well, you would take your 30 milliseconds, you plug it in here for t, and you would do that, but you got to make sure that you convert your 29.4 to radians before you add them together, or your 377t into degrees before you add them together and take the sign. Keep that in mind, but this problem is solved. One more thing before we go, just for the sake of completeness, you need to know. You know how to combine resistors together. Resistors in series, so equivalent resistance, is going to be the sum of the individual resistances from I is equal to 1 to ever how many you have. So this is in series. When we're in parallel, 1 over Req is equal to the sum of 1 over each individual resistance from I is equal to 1 to n. Now when we dealt with capacitors in series, it was like this. 1 over C equivalent is equal to the sum of 1 over the individual capacitances from I is equal to 1 to n. And C equivalent is equal to just the sum of the individual capacitances from I is equal to 1 to n. This was for resistors, this was for capacitors. What about inductors? How do you combine inductors? Well, inductors combine exactly the same way that resistors do. So L equivalent is equal to the sum of the individual inductances. And 1 over L equivalent is equal to the sum of 1 over the individual inductances. Okay? So the inductors combine exactly the same way as resistors do. So if I have an inductor here and an inductor here, and that's, let's say, 0.5 Henry, and this is 0.3 Henry, then the equivalent to that is 0.8 Henry. Okay? But if you're only combining two parallels, let's say you've got these two right here. Let's go ahead and work one. 0.7, 0.3 Henry, both of them. All right. So you can make that into one equivalent. Whoops. Into one equivalent here. This will be the equivalent, and LEQ is product over sum. So 0.7 times 0.3 divided by 0.7 plus 0.3. This is going to be 0.7 times 0.3, 0.21 over 1. So this is 0.21 Henry for L equivalent. There. You see how it works. Okay, shouldn't be much of a surprise. So once again, this is presented so that you can have a complete understanding of how to combine all of these ideal basic circuit elements now. And it also allows me to give you a little more complicated problem than this one right here, because I could do something like, let's add another resistor here. Then let's add a second inductor here, and let's stick another capacitor in here. All right. If I did that, then you could combine those two into an equivalent, those two into an equivalent, those two into an equivalent, and still solve the circuit exactly the same way that we've done. The only difference is you have to recognize what's going on here. You have to recognize what's in parallel and what's in series so that you can combine them using these techniques here. Okay, I think that finishes RLC circuits. In fact, I think that finishes everything regarding oscillations. Let me check. Yeah, next time we'll talk about power and transformers. Okay, we're done.